Hello everyone. In this video clip today, I'm going to go over 3 sections of our textbook. Section 4.7 about optimization problem. Section 4.8 is about method of approximation, and section 4.9 is about antiderivative. So we're going to go over one section at a time. We start with 4.7, optimization problems. What is it about? You're trying to maximize something or minimize something, try to find a maximum or a minimum. We're talking about optimization problem. So I think it's best when I give you an example, and then via example I explain everything for you. And I'm glad that most of the time this type of problems, optimization problem, you guys are going to see a word problem. Means what? You have to read the entire word problem, and then you have to figure out the functions by yourself. Okay? They don't give you function up front. You have to figure it out. So be very careful, because if you don't know how to set up the function from words, then there's no way we can solve. So have to do that first step. That would be the hardest step, I think. And then after having a function, and you're going to use the knowledge you learned before, the first derivative test. Okay, you have a function, you take the derivative, you set the derivative equal to 0, you find the critical value. That will be your maximum or minimum in this type. That was the idea. So let's start with the problem. A very typical one. How about this? Say a farmer, and he has 100 meters of fence, and he want to fence his rectangular farm. Okay, the perimeters. He got 100 meter total. I'm just making up a problem. 100 meters. Okay, so P equal to 100 meter, and his farm is a rectangular shape. How can he fence this area so that he got the maximum area? Okay. Max area. Of course, his farm is much bigger, but he has 100 meters of fencing. He's one of his portion of his farm, and he want to get the maximum area out of 100 meters of fencing. Can you help him to find a way of fencing this area so that he got the maximum area? Okay, so we have a problem right here. We have a rectangle, a rectangular shape. Okay. And so this is the width, it's called the length, and we want to find the maximum area. So the formula that you're looking for is what? The area of a rectangle. And we know that the area of a rectangle is calculated by length times width. Okay, and you know that we can adjust the width, we can adjust the length, so that we have either a very long rectangle or a very short rectangle. Okay, we just want to make sure that the entire perimeter, total length measurement is going to be 100 meters. So we're looking for maximum of this. All right. So we're going to use the information that we have right here. The perimeters is the total measurement of the length and the width. So perimeter is equal to twice of the width plus twice of the length. See, width plus width and length plus length total. And this is equal to 2 times width plus length, and it's equal to 100. Okay, that's all he has. 100 meters. So you can divide by 2, you got width plus length equal to 50 meters. This is half of his perimeter. Okay? So you have the sum of 2 variables equal to 50. I can solve for one variable. Plug in here, I have a function. Say, solve for L then. L is equal to 50 minus W. And in here is the function that we're looking for. We try to find a function of the area, and then we know the area in terms of length times width. So area depends on 2 variables, length and width. Okay. For count 1, we only learn function with 1 variable, so we have to solve on one of the variable in terms of the other variable. So in here I solve for L. L is 50 minus W. So plug in here, I got 50 minus W times W, which is 50W minus W squared. Now area is in terms of the width W. So pretty much my function is the area in terms of W is equal to 50W minus W squared, and it's not hard to see that this is really a quadratic with -1. That's a leading coefficient, so probably upside down. And how do you find the maximum of this? You can take the derivative, and recall what we learned last time. We have to mention what? The domain, right? Width right here, the shortest one is 0. We're not gonna make a fence with zero width, with a negative number of width. Zero is like really extreme already, and the longest one gonna be 100. So W gonna run from 0 to 100. In this particular problem, okay, you only have total of 100 meters of fencing. You cannot make a width of 101 meter. All right, so from 0 to 100, that would be the domain of the function, and you can take derivative. Now the actual problem, I don't use F anymore. This is A, right? Is what? 50 minus 2W, and then this is 2 times 25 minus W, and you let derivative equal to 0. Then you got 25 minus W equal to 0, or W is equal to 25. And recall the first derivative test, you're going to have a table. In here, I'm not using the second derivative test at all because I'm looking for just max or min, so I don't care about concavity. W run from 0 to 100, and the critical value is 25 right here. This is derivative, and this is A. When W equal to 25, the derivative is 0. Okay? When W is less than 25, say W is 24, and then this is a positive number. W is bigger than 25, say 26, and it's a negative number. So the function A going to go up and then go down. So obviously this point right here going to be the maximum. H is not just a local maximum. It is actually local and the absolute maximum at the same time. So by looking at the table, this is the first derivative test, you can say what? You're going to have a maximum area at W equal to max area at W equal to 25. Okay? And 25 is not the area. 25 is the width. The width equals 25. So how do you find the max area? It's 8 of 25, right? The area 25. Function is right here. 50 times 25 minus 25 squared. All right, I guess we need a calculator. Huh? Let me grab a calculator. $50 times 25 minus 25 square equal 625, and this is meter square. So to answer for the question, you say this: if you have 100 meters of fencing and you want to get the maximum area out of it with a rectangular shape, you better fence it with a square. This is 25. This is 25. And of course, this is 25. 25. And the answer is what? With all the rectangles with the same perimeter of 100 meters, the square one will give you the biggest area. Okay? You guys see the entire picture for the problem. You have a story. You try to translate that story into a mathematical function, okay, with one variable. Let's count one variable, okay? And you want to find maximum, you use what you learned before in section 4.3, 4.5. Determine the domain, okay? Take derivative, set derivative equal to 0, okay? Then solve for that critical value. You have the first derivative test, tell you the sign of the derivative and monotonicity when increasing or decreasing, and by looking at the table you can find either a maximum or a minimum, and that point will be the answer. Okay, same idea for all the functions. They may ask you about volume of a sphere, volume of a cone, all kind of things, okay? Minimizing the costs in business, all right, but doesn't matter what, the whole frame, the whole step for setting up the problem is going to be the same. So I'm going to give you one example like this, and hopefully that will be helpful for you guys to learn. Next, I'm going to move on to the next section, 4.8, talking about Newton method. What is it all about? Hang on a second. one of the very important problem in mathematics is how to find the solution. So what value of x is f of x equal to 0. Say for example, I got f of x equal to 2x cubed minus 7x plus 1, for example. It's a cubic. And find the solution means what? Find the zeros, okay? What f of x? In other words, you find x intercept. Say, this has a point right here. Right here. Can you find that point? Okay? And it would be ideal, it would be good if you can find the exact answer. But I claim that most of the time we won't be able to find the exact solution for a function because it's impossible if you don't have a nice enough function. However, in real life we don't really need the exact answer. What we need is what a good approximation of the exact answer. So up to like 4 or 5 decimals, if you can find that way, that's good. So how to approximate the answer close enough to the actual answer. And so Isaac Newton offered a method. We honor him because the Newton method. Okay? So the idea is this. We're going to find some point, say x1. Okay? And then from x1 we get another approximation x2. And then x3. And those x values getting closer and closer to the actual answer. And so after like 4, 5, 6 or a finite many step, you have a very decent approximation of the real solution. And his method is saying this. x2 is equal to x1 minus f of x1 over f prime of x1. So you just randomly choose a first number, technically, somewhere. And you do what? You calculate f of x1, you have a function, right? You calculate f of x1, find the derivative, take the ratio, and then take x1 minus that. You have x2. And after having x2, you do the same thing. Calculate x3 by what? x2 minus f of x2 over f prime of x2. Keep going. Say, in general, xn is equal to x of n minus 1 minus f of xn minus 1 over f prime of xn minus 1. So the next point will be calculated based on the previous point. And before I show you example, let me explain this idea, how they come up with that idea practically. And by the way, this method, there's no guarantee it's going to be working all the time, okay? Sometimes it's going to fail. And we have to choose a different initial point to start over. And even if you choose a different point, it's failing, so we have to find a better method. But at that time, this is a very good method, so we learn it. Say, let me just, you have a function. You try to find this point. Okay, so my x1 is right here. I choose a point x1, and this is my goal. I try to look for this point, x0. I start with x1 right here. And of course, this is x1, this is my function f of x. So this point right here will be f of x1, okay? So if I have a point on the graph, let me write somewhere. x1 comma f of x1, and I can find the slope of tangent line go through this point. Let me use green color. This is my tangent line. Okay? And how do you find the slope of that tangent line? Slope is f prime of x1. Was that right? Derivative. Okay? And can I find the equation of this line if I know the point and I know the slope? Yes. The equation of the line is what? Y minus y1 equal to m times x minus x1. Y minus y1 equal to slope times m x minus x1. This is the equation of that tangent line right here. All right? And this is my x2, the point that I'm looking for. And you guys see that x2 is getting closer to x0 compared to x1. So how do I find x2? This point is on the line, y 0, so I'm looking at y equals 0 right here. I got 0 minus f of x1 equal to f prime of x1 times, this x now is x2, right? x2 minus x1. The point is 0, comma x2. This is, oh, I'm sorry, I wrote it backward. x2, comma 0, x first. Right? x2, comma 0. So y here is 0, and x here is x2. You plug in, you have this equation right here. All right, solve for x2. Divide f prime on both sides and then add x1, you got x2. You have this. And then after having x2, of course, the same step over, you have x2 and f of x2. This one x2 right here, this is f of x2. You draw another tangent line, let me use red color. Tangent line right here. This is x3. Right? Same way, y minus fx2 equals f prime of x2 times x minus x2. Plug in y equals 0. You have x3, and you have another point right here, and then you draw another tangent line, and x1, x2, x3 keep getting closer and closer to x0. After a couple of times, you have a very decent approximation of the intersection. In other words, you're getting closer to x0. Okay, that's the whole idea for Newton's method. And let me give you an example. And choose an easy one. Okay. Example. F of x is something that you guys all know. Equal to x squared, as x squared, right? X squared minus 1. Make it easy. And the graph is this. This is -1 right here. This is -1 right here. 1 right here. It has two x in the set, two solution. X equal to 1. X equal to -1, right? Assuming that we don't know those answers. We want to find the answer. Say 1. So, well, 1 is too nice. How about we start with x equal to 2. x1 equal to 2. We calculate f prime. First of all, f prime of x is equal to 2x, right? All right. So the formula is what? x2 is equal to x1 minus f of x1 over f prime of x1. So we start with the point 2 right here. 2 somewhere right here, 2. Okay? And hopefully from 2 we go all the way to 1. So this is 2. So 2 minus f of 2 right here. F of 2 is, how much we calculate this? F of 2, 2 squared is 4 minus 1 is 3. Over f prime of 2 is 4. So x2 is equal to this. And this is 8 over 4 minus 2 over 4 is 5 over 4, I think. Okay? So we start right here. x1 equal to 2. We calculate x2 is what? 5 over 4. Very close right here. This is x2. 5 over 4. Now we can calculate x3, and I claim it's going to be closer to 1. x3 is x2 minus f of x2 over f prime of x2. And x2 is 5 over 4 minus f of x2, so we plug in here, 5 over 4 squared minus 1, 25 over 16 minus 16 over 16 is 9 over 16, right? 25 over 16 minus 16 over 16, yeah, 9 over 16 over f prime of x2. So f prime right here is 2 times 5 over 4. So it's 5 over 2 over 5 over 2. And you simplify. Okay. This is 5 over 4 minus, this is 9 over 16. 9 over 16 times 2 over 5, cancel out, this is 8, so what? 9 over 40. So this is 50 over 40, minus 9 over 40, this is what? 41 over 40. Oh, very close to 1. You see, only 2 steps. I have something very close to the exact answer. And of course, you want to go one more step, you have even better approximation for x equal to 1. Okay, that was the idea. And that's all about 4.8, called Newton method. So one more time, Newton method is a method that helps you to find a solution, or graphically the x-intercept. And the general formula that I gave you already is the one. The next term, xn, is equal to the previous term minus the fraction of the function over f prime of x and minus 1. Okay? And this is all about 4.8. And again, knowing the formula is one thing, understanding the formula is another thing, practicing is another thing to master your understanding. All right. Now, let me move on to the next section, 4.9, which is the last section of chapter 4, and we're going to learn antiderivative. And I want you guys to take this section seriously, 4.9. So for the next chapter, chapter 5, we'll talk about integral and the fundamental theorem for calculus, and it's all about antiderivative. So far, we learned about derivative. Say I got a function, f of x, say equal to 2x. If you want to calculate the derivative of 2x, called f prime, right? F prime of x, derivative is 2, is that right? So now we're going to do the opposite of it. Instead of finding the derivative, we find the antiderivative. In other words, what is a function so that the derivative is equal to 2x? Okay? So antiderivative, let's call it big F then, big F of x, is a function so that when you take the derivative of big F, you want big F derivative is equal to 2x. Okay? So what kind of function when you take the derivative equal to 2x? So we don't take the derivative function, we do the antiderivative. And the answer is x squared. You guys see? Because x squared derivative is going to be 2x. But that's not enough. X squared plus any constant, that would work. You know why? Because the derivative of constant is 0. Okay? So that is the whole idea of 4.9. You find the antiderivative of a function. Okay? So the step backward, that's what we learned before. So let me just give you some basic function, antiderivative function, okay? And we just practice to get through those. So f of x, and then big F of x. Okay. So if this is x, start with first one. If x is 0, then antiderivative of 0 is a constant c. You see why? Derivative of any constant is 0. If f of x is equal to 1, antiderivative of f of 1 is x plus c. Because the derivative of x is 1, the derivative of c is 0. Okay? This is x. Antiderivative of x is 1/2 x squared plus c. You guys see why I got 1/2 right here? Because I want to cancel out the 2. Take the derivative. We got 2x, right? Times 1/2, just x. Okay, so in general, x to the n, antiderivative is going to be 1 over n plus 1 times x to the n plus 1 plus c. And you can check it out by yourself. Take the derivative. N plus 1 over there, and cancel out with the n plus 1, and then just x, and then constant c, derivative is 0. Okay? So, what about cosine of x? You ask yourself, what function would I take the derivative equal to cosine? Gonna be sine x, and don't forget plus c. Okay, I'm running out of room, so let me go over here. Do the same thing. F of x, big F of x. We got cosine, and then let me write sine here. So sine x, guess what the antiderivative sign? Negative cosine of x and plus c. You see why we got negative? Because the derivative of cosine is negative sign, and with the negative, make it positive. Okay? This is e to the x. This is e to the x plus c, right? Derivative of e to the x is e to the x. If this one is 1 over x, what function take the derivative equal to 1 over x? It's ln of x plus c. So far, so good. What else? If you have f of x is secant x, tangent x, derivative of tangent x will do the work, do the job. Tangent x plus c. Okay? This is secant square. The derivative of tangent is secant square. Let me double check. Oh, backward. This is secant x. This is tangent x. Take it back, guys. See, I mess up. and so forth and so on. Do you fill out a table, right? Just the opposite step of tangent of derivative. So let me show you some example. To graph up the video clip. Okay. Let's start with the first one I see in the book, which is a very easy one. If you got f of x equal to 4x plus 7, find the antiderivative of this. Okay. So big F of x. 4 is a constant, you leave it alone. Antiderivative of x is 1/2 x squared. Of course, later on, you can see right away this is 2x squared, right? And plus 7, now 7x, and then plus the constant c. See, 7 the constant, derivative make equal 7 is 7x, right? And derivative make 0 is the constant. So this is what? 2x squared plus 7x plus c. This is your big F. Take the big F, for sure you have small f. Okay. Let me show you a very popular type of problem in this section. I'll look for one. Okay. Ask you to find f. Okay, they give you this. F double prime is equal to 20x cubed minus 12x squared plus 6x. All right. So from f double prime, you got to go back to f. We do step by step. From f double prime, go back to f prime. That's right here. Okay. This is 20x cubed, right? So 20 is a constant outside. X cubed, go back to f prime, go to x to the 4, and then you got 1/4 in front. Because the derivative of 1/4 x to the 4 is going to be x cubed. And minus 12x squared, so anti-got x cubed, and you got 1/3, I say. 1/3 in front. And I claim later on you guys are going to do much faster, but this is assuming the first time, so we do it step by step. And then x is going to be x squared, 1/2 in front, and you got number 6 in front. And then don't forget to add a constant. Simplify. 5x to the 4 minus 4x cubed plus 3x squared plus c. All right, one step further. F of x. This time we're going to do quick, right? Derivative of 5x to the 4 is x to the 5th. Derivative of 4x cubed is x to the 4. 3x squared, derivative is x cubed. And then what? Antiderivative constant is cx. And then plus another constant, let me call it d. See? And c and d are constants. Okay, try another example. Same type, but we're going to add more information into it. Find function f. I'm going to give you this. F double prime of x is equal to, where am I looking at? Negative 2 plus 12x minus 12x squared. Negative 2 plus 12x minus 12x squared. That is what I got in here. They give f0 equal to 4 and f prime 0 equal to 12. F of 0 equal to 4 and f prime of 0 equal to 12. Okay, so the difference between this one and the previous one is what? We don't just leave c and d as constant. We have to actually calculate c and d. And in order to calculate c and d, we have some initial conditions right there. So let's start. If this is f double prime, then f prime of x will be negative 2x plus 6x squared. You see why? Derivative of negative 2x is negative 2. Derivative of 6x